So let's consider this problem here next. We've got a square, side length of just S. Don't know specifically what the side length S is. We're just going to call it S. And the area is changing as time passes, so could be expanding, could be contracting, whatever. Well, A here on this next handout problem, write dA over dt in terms of ds over dt. All right, so this is gearing us up for some bigger and better things to come, but I want to write dA over dt in terms of ds over dt. So one thing about these problems is a lot of times the formula is not supplied. And so we may have to come up with an equation on our own. Well, this is a square and we're talking about the area. And so that's a fairly common equation. The equation is area equals side squared. For the area of the square, you got side squared. So that's step number one. Now, in this case, write dA over dt in terms of ds pretty well spells out what we need to do here is take the derivative of both sides, right, with respect to t. So ddt both sides. All right, so that's a derivative of that would just be 1, right, because you bring down the power and the new power is 0, so it would just be 1. But I'm doing the derivative with respect to t, so I also would need dA over dt with that. And then the right-hand side, well, it's s squared, so I do the power rule, 2s, but it's a d over dt, so I'm doing the derivative with respect to t, so I also need ds over dt. And that accomplishes our goal here because we were to write dA over dt in terms of ds over dt. There you go. That's all it wants. Now B has a little more to it. All right, so what is the rate the area is increasing? If the sides are increasing at a rate of 6 centimeters per second. Abbreviating here since you got it on your paper anyway. And the sides of the square are 30 centimeters long. So we've got some information here provided, but we're seeking the rate the area is increasing. Well, what is this asking us for? Again, it's asking for a rate. It's not asking for an area. It's asking for the rate the area is increasing. So what is that seeking? What are we looking for here? The rate. That's the derivative, isn't it? I'm looking for dA over dt. The rate at which the area is increasing. So that's what I'm looking for. What I provided here, the sides are increasing at a rate of 6 centimeters per second. So that's not giving me the side length. That's giving me the rate of the sides changing. So that would be 6 would be the ds over dt, right? The derivative. And this is then s. The sides are 30 centimeters long. So I'm looking for dA over dt. I've got ds over dt. And I've got s. Well, we just so happen to have a relationship, the equation that gives me dA over dt, so we use that. Okay, did our work for us there. So we're going to use that, which came from the area formula, but yeah, so just plug in those numbers. Oops, it's the other way around, but doesn't really matter. This one, but good. So that is 360. 12 times 30, 360. Now, what about the units here? Well, they're really pretty easy because this notation kind of spells it out. The units of this are going to be the units of A over units of T. And in this case, we're talking about the area of a square. So area units are squared units. And in this case, we're dealing in centimeters, so it would be centimeters squared. Write that down. Okay. So the units are units of A over units of T. So in this case, area units would be centimeters squared. Then the units of T, well, it's telling me here times in seconds. So just to get that all squared away. Okay? Is that all right? All right. So number 2 is the volume of a sphere with radius r expands as time passes. So we're talking about a sphere. So the volume expands. It's increasing as we go along. It's blowing up there. Find the rate at which the volume is changing when in terms of the rate at which the radius is changing. Well, that's very similar to previous problem, A part. All right, so we're talking about a sphere and its volume. If you have a formula you're not familiar with, look up in the reference pages in the book there. They have little gray edges or blue edges or something. You can look those up. If you're not familiar with the formula, those are provided on those reference pages. Just FYI there. But in this case, the volume of a sphere, 4/3 pi r cubed is what we're dealing with there. And so again, I'm looking for the rate at which the volume is changing. So I'm looking for dV over dt. So I need to ddt both sides. So this side, the dt of that would be dV over dt. And then over here, 4/3 pi is just a number. And so I'm just dealing with the r cubed as far as the derivative is concerned. So it'll be 3r squared. But I'm doing the derivative with respect to t, so I need dr over dt with that. And so that's a pretty good answer, but, clean it up. The 3's cancel, so it's just dV over dt equals 4 pi r squared dr over t. And that's what we're looking for there. Is that okay? All right, number 3. If the area of a rectangle is decreasing at a rate of 4 meters squared per second, so the area is decreasing at a rate, what does that tell me? Well, that's telling me dA over dt is negative 4 meters squared per second. That's what that first piece of information. And the length is increasing at a rate, so dL over dt, it's a rate at which the length is increasing. It's 1.5 meters per second. That's what that first bits of information tell me. So let's find the rate at which the width is changing. So the rate at which the width is changing, that's dW over dt, right? What is that? When the length is 10 and the width is 8. So that's the information provided on number 3. Well, okay, I'm looking for dW. So this is this is a good example of what these problems are like. They'll give us some information, and they probably won't give us the equation, so we have to come up with the equation ourselves. In this case, I'm dealing with a rectangle, right? Area of a rectangle, oh, that's an easy one. So start with that formula. Now, very important note here. Unless we have a fixed variable, so it's a constant kind of thing. Unless one of the variables is fixed, you can't plug in numbers yet, okay? So unless a value is fixed, i.e. it doesn't change as other things change, don't substitute until after taking the derivative. You can plug, if a number is fixed, the value is fixed, you can substitute it in up front, and that because it makes things a whole lot easier as far as your derivative goes. But if it's not fixed, you don't want to substitute. Here's what I'm saying. The area of this thing is decreasing. So the area is changing, so it's not fixed, obviously. But by implication here, the length and the width are also changing. The length is actually increasing, so the length's getting bigger. And we're wanting to know what the width rate of change is, so it's also doing something. And I'm guessing it's going to be decreasing since the area overall is decreasing. But you see what I'm saying? The length and the width aren't fixed. They're changing. Don't plug in either one of these numbers yet. That's what I'm saying. Because that would make the derivative a whole lot easier, but it wouldn't be right. Okay. All right. So we're going to need to do the derivative first here. There's nothing to plug in. Sometimes we can plug in numbers, but not on this one. So forget about all these values right now. We're going to take the derivative with respect to t of both sides, all right? So this side is 1, but it's dA over dt. We need that. What about this side? LW? Doing the derivative of it? What rule? Product. Yeah, we got a product rule. All right, so the derivative of the L would just be dL over dt, since the power rule just gives us 1, but it's just times W. I don't do the derivative of that yet. Then I do the L times the derivative of the W, which would be dW over dt. Yeah. Product rule for that side. Now we can start substituting. We know actually we know dA over dt is -4. dL over dt is 1.5. The W, you know, is 8. The L is 10. And the dW over dt, well, that's what we're trying to find. So we just solved that for dW dt. That's -4 equals, was that 12? Plus 10 dW over dt, is that right? So subtract 12, -16 equals 10 times dW over dt. And divide by 10. So we've got -16 over 10, -8/5, 1.6, however you're going to write that. Units wise, let's write it this way. All right, so we've got dW over dt. And however you want to write it, -1.6 or but units wise, yeah, we're dealing with area, but in this case I found dW over dt, so it'd be the units of W, which that would have the same units as the length here. The length is in meters. Well, it gives me the length, yeah. It's 10 meters and 8, so the width's in meters. So this is meters per units of time, in seconds. So. All right, good on that? Let me do one more. Today here. Is that all right? Question? Tank is in the shape of a box. We got a box. The base, with a base that is 15 feet by 20 feet. Height is 10 feet. Okay? And it's being filled with water. If the height is changing at a rate of 2 feet per minute, what is the rate the volume is changing? Okay, well, let's kind of draw the picture here, maybe helpful. So we've got a box. The base is 15 feet by 20 feet, and the height is 10 feet. I didn't draw it to scale, so sorry about that. But, so I'm filling this thing with water. It's creeping up. So the question is, what's the rate the volume is changing? The rate the volume is changing if we've got this information here. Well, all right. This one's a good example to compare with here, number 3, and what we can substitute and when. All right, so we're looking, so the height is changing at a rate. That would give me what information? That's not the height, that's the height changing rate. That's dH over dt, isn't it? I'm looking for the rate the volume is changing, so what am I looking for here? dV over dt, right? That's what I'm looking for. Okay? Now, I need a volume equation. Well, I'm talking about the volume of a box. And volume of a box is just length times width times height. So it's fairly simple. Now, in this particular case, though, by implication, remember my little note on number 3. Unless a value is fixed, don't substitute it until after taking the derivative. Well, what that means is, if it is fixed, substitute it in before you take the derivative, because that's going to make things a whole lot easier. If it is fixed, meaning it doesn't change throughout the time, do substitute it before taking the derivative, because that'll make it a whole lot easier. And do you see here we've got 2 values. Actually, we've got 2 values here we can substitute. Which values are fixed here out of this formula? As time progresses, the thing's filling up. What's changing? Because this would be, that's 10's the overall height, but the height we're talking about here is this, the height of the water. So it's changing, the height is changing. But what's not changing as it goes up? The length and the width, right? The length and the width, no matter where that water level is, the length and the width are the same. It's always 15 and 20. The height doesn't get to 10 until up here, so the height is going up or down. So the volume's changing, and the height is changing, but the length and the width aren't changing. So those are fixed. This box isn't growing by length and width. It's just we're filling the box up with water. So the height's the only thing that's changing. These are fixed. So that means I can substitute them in before I do the derivative. Is that okay? That's 300h. And you see how that's going to make this derivative a whole lot easier. Because instead of having 3 variables over here, I just have h. Yes? With me? Okay. All right, so now we ddt both sides. And so we've got dv over dt equals 300 times the derivative of h, so that would be dh over dt. And so the dv over dt equals, I know dh over dt is 2 right here. So it's 300 times 2. So dv over dt equals 600. And the units would be the units of volume, which in this case, volume is cubic units. So the units here would be as feet, is the base unit, so it'd be feet cubed. And then the units of time, well in this case, looks like times in minutes. Okay? Good with that? Well.